The theory of relativity can explain the relationship between electric fields and magnetic fields. Electric fields and magnetic fields are closely related, and when an electric field changes, a magnetic field is generated, and when a magnetic field changes, an electric field is generated. This relationship is one of the important consequences of the theory of relativity. The theory of relativity explains the relative characteristics of time and space in the universe, and electric fields and magnetic fields are also influenced by this relative nature of time and space. Through this, the theory of relativity explains the relationship between electric fields and magnetic fields and demonstrates the transformation between them. Furthermore, the theory of relativity shows that electric fields and magnetic fields can be seen as one electromagnetic field, which is a fundamental principle of electromagnetism. Therefore, the theory of relativity is a very useful theory for understanding the relationship between electric fields and magnetic fields. Electric fields also propagate at the speed of light. This is explained through a very important concept in the theory of relativity called electromagnetic waves. Electromagnetic waves are waveforms in which electric fields and magnetic fields propagate as they intersect each other. These electromagnetic waves progress at the speed of light. Therefore, electric fields are also generated at the speed of light, and electromagnetic waves and electric fields are closely related. Additionally, through theoretical predictions such as ensemble averages, we know that electric fields can propagate through a medium at a speed slower than light. However, in general, electric fields in space propagate at the speed of light, and electromagnetic waves also progress at the speed of light. Although electrons move slower inside a wire, it does not lead to the generation of electric fields or magnetic fields. The electrons inside the wire are influenced by the electric field and move accordingly. The electric field plays a role in inducing the motion of electrons inside the wire. The movement of electrons inside a wire is a concept separate from the motion induced by the electric field. The generation of electric fields inside the wire occurs when current flows, causing the electrons to move. Additionally, heat can be generated due to the resistance that arises from the movement of electrons inside the wire. When the temperature inside the wire increases due to heat, it can affect the motion of electrons. Such influences can lead to changes in the properties of electric fields or magnetic fields. However, these effects generally act at a negligible level, and the primary causes of the generation of electric fields or magnetic fields are the current and electric fields inside the wire. Electric fields propagate at the speed of light, and electrons move accordingly. However, inside the wire, electrons interact with resistance, which slows down their motion. Therefore, even though the electric field progresses at a constant speed inside the wire, a phenomenon can occur where the density of electrons increases within the wire. The electric field induces the motion of electrons inside the wire, causing the flow of current as the electrons move within the wire. The resistance within the wire resists the motion of electrons, leading to a decrease in their velocity. This becomes one of the reasons for an increase in electron density. When electrons move inside the wire, collisions with other interacting electrons also contribute to a decrease in their velocity. These collisions can dissipate the energy of the electrons, resulting in the generation of heat. Therefore, it is important in electrical system design to minimize wire resistance and ensure smooth flow of current. Yes, according to the theory of relativity, as an object's speed increases, its length contracts relative to an observer. This is known as Lorentz contraction. Therefore, if the velocity of electrons inside the wire were to increase, their length would contract relative to an observer, potentially leading to an increase in density. However, this contraction occurs at very small levels, so the impact of electron length changes on the overall increase in wire density is minimal. Additionally, the increase in density resulting from the faster motion of electrons inside the wire is influenced by various factors, such as interactions between electrons and the electric field, and the temperature inside the wire. Hence, it is not solely caused by the length change of electrons.